Okay guys, welcome to my YouTube channel. Today I want to talk about hybrid orbitals, and I try to manage it in a rather not very lengthy time. So we would like to talk about the shape of the orbitals. So orbitals are sublevels of atomic layers, and we've talked about the atomic layers, the periods that you see in the periodic table. Each of those periods have different sublevels naming S, P, D, and F. Each of these sublevels have real uh, orbitals in them. Each individual orbital have the maximum capacity of 2. So S is just a spherical orbital with the capacity to host 2 electrons, one spin up, one spin down. It's easier for the chemist, so it's rather a spherical like this, and uh, the capacity is, as I told you, is just 2 electrons. But chemists would also love to actually represent any s. Let's say it's 3s orbital, and if it's 1s, it's just the smallest sphere. It becomes bigger and bigger if it goes 2s or 3s. So if it's 3s, 4s, whatever, they just use a box and then say one orbital up, one orbital down, and this is a spin up, so that a spin up, a spin down, so the 2 electrons can rotate and live together, not repel one another. Because when electrons certainly have charges, and if they actually um, if they rotate in the same direction, they would repel. P orbitals, they are dumbbell shaped. There is one in the y direction, if this is y, and we took this one coming out of the board as x, and the y going up as z. So there is one in the z direction and one in this direction, so there is 3 of them. So if it's 2p, for example, you could actually have the shape of, how to say, the shape of 3 boxes together. And if you want to put electrons in this p, this was p6 that I just showed you, electrons first don't want to pair. So if you put 2p2 for example, that would be 2 electrons, and the next one would go to the next empty orbital, so 2p3, and as you go to the 2p4, the pairing actually happens with a spin down electron. So you could do 2p4, 2p5, and 2p6. That's how you fill them up. D orbitals, there are double dumbbell shapes like this one here, and you could see that there are 2 dumbbells in a page sort of thing. So if the page is xy, there is one in the x direction and one orthogonal. So this is one orbital, one d orbital, that you might call it, if this one is x and the other coordinate you call it y, you could say it's d x2 y2. Okay, there is also one other peculiarly shaped orbital called dz that I have a representative of it. It's just a donut shape around a dumbbell. This is called dz, and it's, as the name implies, it's in the z direction. So if you have this one, this guy should be in the z direction, and they call it the dz orbital. There are 5d orbitals, and if you want to represent the 5d orbitals, you have to put a large box with 5 boxes, 2, 4, 5, 1, 2, 3, 4. Let's say this is now d4, and d5, 6, 7. This would then be d7. Okay, so that's how it goes. And the story about orbitals, these are AO, so to speak, or atomic orbitals. Now we could certainly mix these orbitals to get kind of molecular orbitals that you see kind of rotating in the background in my preview desk that you could see on my desktop. So we talked about the atomic orbitals. Let's also talk about how do they mix. When we do mix them, F orbitals, the shapes are going to be just like porcupine, many of these dumbbells, and they have strange shapes. You could Google it, you could actually see models for it, but it's not we're not very interested in talking about their properties. We do, however, want to know that the F orbitals have 7 Also this one, 1 2 3 4 5. Let's add two more. One in the beginning to make it 7. So 7 of those, and we never use this kind of thing to do electronic configuration. Remember, we did electronic configuration and sort of full electronic configuration for a small number of electrons. For example, like for neon 10, we could do full electron configuration, or we could do noble gas configuration. For those that we do balanced shell, let's just go to one example that I have handy right here in my notebook. Let me just find one example to show you what is the third sort of electronic configuration. It's the one that is independent, my bad, that is not independent, and you have to do it after doing the electronic configuration. So I'm going to write down real quick an electronic configuration and then talk about it real fast. So imagine you have chromium 24 and it's argon 4s1 3d5. I just told you how you put the D and the D5 or S, so I just do 4s here and 3d here. I don't say the number of electrons as I did previously. This is, by the way, called 2 4 5. This is, by the way, called the valence shell orbital diagram. Orbital, I could just write down orbital diagram instead of doing this, but I just want to move fast. Orbital diagram. Okay, so the orbital diagram is 4s1, so 1 electron here, and 3d5 is 1 2 4 1 2 3 4 5. That's the 4s1 3d5 in the form of the third notation of electron configuration. You can't do this alone. It has to be done for an electronic configuration for which you have done the noble gas notification first, the noble gas notification electron configuration first, and then you could do this as a complementary. So that I wanted to actually mention out. Let's now go about mixing, which mainly happens for molecules rather than atoms. Okay, so we do have these kind of electrons. Let's see, and I do want to talk about their properties as well. Okay, so now let's go on to the idea of mixing these orbitals. I want to point out the mixing of the s orbital and p orbitals. Okay, so we could mix s with 1 p orbital, s with 2 p orbitals, let's say px py, s with 3 p orbitals, all the p x y z, s 3p and a d, and then s 3p and 2d. Okay, this will give you the s and a p. A p is elongated. When you mix it, the result is going to be 2 orbitals, because you mix the number of the orbitals you actually mix is going to get you to produce the same number of molecular orbitals. This we call MO, and this we call AO. So atomic orbitals and molecular orbitals. Let's just quickly talk about this. So the MOs, if you have S and P, you could get 2 orbitals called SP, and they're in one line. Okay, we cannot have that sort of configuration if we just assume that we have this. Those would be a good representation of sp orbital. Okay, if you mix s with 2p orbitals, the results then would be in a plane, trigonal planar, and it would be this. The result would be 3p orbitals. Now the px and py should be already those that are in the plane, so it's py and px. Let's say this is py and px in the x direction and y direction, and it's in a plane. When you mix them with a s orbital, it gives you this sort of configuration. I have a representation of that, and it's just like this configuration that you could see here, it's in the plane, and there are in the three different, how to say, three different, as you note, it's kind of in three different forms. So you could see that I have the x and y that was previously in this plane, as you could see there, and then when I mix with the s orbital, I get this sort of configuration. So that's the idea of three, actually the hybridization of, or the MO diagram of sp2. This we call sp. Now the name of the MO orbitals is just sp, and their number goes in the top. So we have sp2. This means that we have mixed 1s with 2p, and how many of them we have? We have two, my bad, sp1, like one we don't write, sp, and we have two of them. This we call sp2, means we have mixed 1s orbital with 2p orbital to get three of sp2 orbitals that are in this sort of, how to say, in that sort of orientation. Okay, so that's that, the sp2 orbital. We could mix 1s orbital and 3p orbitals. That would go in a sort of tetrahedral arrangement and would result in a little bit more elongated, because when the character of p raises, like there is 1p, 2p, and 3p, it's more and more the orbital generated orbitals are more and more like the p orbital elongated. Okay, so this is like the shortest, and these are a little bit elongated. And sp3 also, we call it sp3 because now we have mixed 3 p orbitals, and we have 1, 2, 3, 4 of them. And this also have a representation of a tetrahedral, and this is what you get. Okay, three, just like in a tetrahedral fashion, you have this kind of sp3 orbitals, and you could see that this is now 4 of those sp orbitals. If we mix 1s orbital and 3p orbitals and 1d, you could have the trigonal bipyramidal form that we saw, and that is 3 just like this in a plane. Okay, and then one on the top and one on the bottom, and that would be 5 sp2d orbitals. Okay, sp2d orbitals then would look like just this orange balloons that I have prepared here. So you could see that in a plane, I've got 3 of those orbitals in this plane that you could see. Okay, one on the top and one on the bottom. So that's how you actually talk about a hybridization sp2d. Okay, any atom that wants to have this trigonal bipyramidal, any molecule that wants to have this trigonal bipyramidal framework, the central atom should be hybridized like this. It should have these 5 orbitals. These are the 5 locations or sites that we talk about them. And remember, when we talk about Lewis structure, we told you that the electrons preferentially go to these locations. That's why if all the 3 were occupied with electrons, you kind of have a linear geometry. If one of them is a lone pair, you kind of have theta geometry. If 2 of them are lone pairs, then you would have sort of a T-shaped geometry. So that's sp2d, and you could also have the last form that is 3 p orbitals and the 2 of d orbitals, and then you will have the octahedral geometry. Okay, with 4 of those in a plane and 1 on the top, and you would have 6 sp. Sorry, this is sp3 because you have to have 5. Yeah, you have mixed 3. So sp3d2. Okay, so sp3d is this one that I just showed you, and sp3d2 is this one, which you have in a plane 4 of those, and 1 on the top, 1 on the bottom. That is the octahedral geometry that you sort of see. So this octahedral geometry, if you look, is kind of the lone pair preference for those molecules go on the top and in the bottom. So XEF4, for example, would have these 2 being occupied by lone pairs, so you don't see them, and it's a square planar with 4 fold rings in this plane, or so to speak, equatorial positions. Okay, if you have just one lone pair, that would be one of these, and that's why we call a square pyramidal, as there is a pyramid. Okay, and that was the case, for example, with IF5. Okay, that's how we talked about the molecular geometries and molecular orbitals. I want to wrap it up here, and next we will talk about orbitals, that we how to discern orbitals. So this is to know the orbitals and the shape of them, but later on I want to use the idea of the sp3 orbital and sp2 orbital and also the sp orbital. So these three are the ones that you want to be able to go into different molecules and be able to actually how to say, find them, locate them, learn about them. Let's wrap it up here, and next I will talk about the um, how to say, the real organic molecules, because these are the ones that actually happen in hyperactivated molecules. So we seldom talk about them, just you should know their shapes, and these three are the ones that we vastly talk about. Carbon can get all of these three different how to say, hybridizations, these molecular orbital shapes. We also call them hybridizations. Here you have a sp, sp2, or sp3 hybridization, with this one being sp2, this one being sp, this one being sp2, and this one being sp3. Okay, now let's wrap it up here, and I'll talk another session about real organic molecules.